Another way to compute the energy of a reaction is to look at the standard enthalpies of formation. We already talked about standard state a little bit, and we said that this little knot up here is like, what is the preferred state at a particular temperature, usually 25 degrees C. And these standard enthalpies of formation are the change in enthalpy accompanying the formation of 1 mole of a compound from its elements with all substances in their standard states. So remember, these guys are state functions. It doesn't matter how you get there. It just matters where did you start and where do you end up, right? And so here we're looking at standard enthalpies of formation. It says, like, under these conditions, right, basically you're saying if I'm assembling a molecule from its component elements, how much energy did it take? And then if I'm doing a chemical reaction with those, basically you're saying I've got molecule 1, I know how much energy it took to make it. I'm going to break it back down into its atoms. I got molecule 2. I knew how much energy it took to make it. I'm going to break it back down into its atoms. And then I'm going to reassemble those to make whatever product I've got. Right? So all this is like, I know how much it takes to make it in a standard state for my reactants and products. And eventually what we'll do is we'll just do, just like we saw with bond enthalpies, I'm going to look at final and initial, and that's going to give me my overall reaction. Right, so our delta H naughts are the corresponding process occurring under standard conditions. Our standard state is a precisely defined reference state. So 1 atmosphere, 25 degrees C. So for example, in here with this reaction, we're going to take carbon and hydrogen, and I'm going to form 1 mole of substance, CH4, methane, and I'm going to get standard enthalpy of formation of minus 74.8 kilojoules. Right? So our definition for standard is that 1 atmosphere in gases, it's got to be a pure solid or liquid for the condensed phase stuff, a concentration of 1 mole per liter for substances in a solution, and elements from which the elements exist under conditions of 1 atmosphere and 25 degrees C. Right? So our characteristics of enthalpy of formation, or that enthalpies of formation, are always given per mole of product, with a product in a standard state. Right? So here we've got 1/2 a mole of N2 gas is reacting with 1 mole of oxygen gas to give us 1 mole of NO2, and we've got a enthalpy of formation of plus 34 kilojoules per mole. These predetermined delta H naught sub F values are standard enthalpy of formation values can be used to calculate the enthalpies of reactions. So delta H of reaction. Hess's law can be implemented to choose any convenient pathways from the reactants or products, right? But you need to know what those individual, reaction A, B, and C are to give you your overall reactants. This enthalpy of formation is like, okay, if I'm working under standard conditions and I got a table of these standard formations, I can just use that table instead of having to do Hess's law. So what you're doing in this combustion of methane then is you got some methane, right? You've got some oxygen. You're going to break your methane down into its component elements. You're going to take your oxygen gas, break it down into its component elements. You're then going to recombine your elements, carbon and oxygen, to make CO2, and oxygen and hydrogen to make H2O products. Right? So you're taking your individual reactants, breaking them down into their elements, recombining them to form new products. Right? So this is just looking at that visually, right? But putting some numbers in it. Right? So we've got our individual reactant here of our methane. Right? It's got a standard enthalpy formation of 75 kilojoules per mole. We're going to break it down into its component elements. We've got our oxygens, right, which are going to have a standard enthalpy of formation of 0 kilojoules per mole, just like any element would. We're then going to recombine some of our oxygens and our carbons to form carbon dioxide, which is 394 kilojoules per mole. We'll combine some hydrogens and some oxygens to form water, which is going to give us minus 572 kilojoules per mole. So all we got to do is look at the sum of the reactants and enthalpies of formation and our products' enthalpies of formation. The enthalpy change for a given reaction can be calculated by subtracting the enthalpies of formation of the reactants and the enthalpies of the formation of the products. You're going to multiply the enthalpies of formation by integers as required by the balanced chemical equation, right? So we need that BCE. Elements not included in the calculation because the elements require no change in form. They're already as elements. So something like O2, N2, Ag metal, lithium metal, right? They're all already in their elemental form. So for our enthalpy calculations, when a reaction is reversed, the magnitude of delta H remains the same, but its sign changes. When the balanced chemical equation for a reaction is multiplied by an integer, the value of delta H for that reaction gets multiplied by the same integer. The change in enthalpy for a given reaction can be calculated from the enthalpies of the formation of the reactants and the products using this equation. So we'll take the standard state enthalpy of reaction is going to be the sum of the enthalpies of formation of the products multiplied by whatever coefficient we need, minus the sum of the enthalpies of the reactants under standard conditions, and times whatever that is. And if you look at products minus reactants, right, this is going to be final, because they end up as products, minus initial, right? So this is very similar to those delta functions we've already seen. And that makes sense because enthalpy is a state function. Elements in their standard states are not included in the delta H reaction calculations, and the delta H naught of formation, or standard state enthalpy of formation for an element in its standard state is 0 already. All right, so let's look at an example. Using the enthalpies of formation, calculate the standard change in enthalpy for the thermite reactions. We got 2 aluminum reacting with iron oxide to give us aluminum oxide and iron. This reaction occurs when a mixture of powdered aluminum and iron 3 oxide is ignited with magnesium fuse, and this is used, for example, to weld together railroad tracks. So our objective, we're going to calculate delta H of the reaction. So to do that, we've been given a delta H naught for the iron oxide. We've got a delta H standard state enthalpy of formation for the aluminum. We've got an enthalpy of formation for the solid aluminum and for the solid iron, which are both 0 because they're already as elements. So the equation we need is that our overall enthalpy of reaction is going to be the sum of the product's enthalpy formation minus the sum of the reactants enthalpy, standard state enthalpies of formation. So for our aluminum oxide, I'm going to take this standard state enthalpy of formation for aluminum oxide. We're going to subtract the standard state enthalpy of formation for iron oxide. Remember, we've got those other elements in there, but they're all going to be zeros, plus a 0 and plus a 0. So we'll have minus 1676 kilojoules minus negative 826 kilojoules, and we get minus 850 kilojoules per mole. And this reaction is so highly exothermic that the iron produced is initially molten, right? So it's going to come out as a liquid just because you're melting it. And this process is often used as a lecture demonstration, as well as in welding massive steel objects like ship propellers or iron in railroad tracks. And we already did bond dissociation energy when we talked about lattice energy in a couple of chapters previous, but I wanted to bring it up here again because I feel it really belongs with all of the other thermo stuff. So we've got Hess's law, right? So Hess's law is I've got several equations, and I manipulate those, and I'm going to calculate some sort of delta H of reaction. And we just learned about the standard enthalpy of formation, where we're going to take our molecules, break them down to atoms, and then reassemble them. So this is looking at things on the molecular. And we're going to use that to find an enthalpy or an energy change of reaction, right? And again, another way to do that is to look at our bond dissociation energy. So here in bond dissociation energy, we're going to look at our change in bond dissociation energy. We're going to break our bonds and reform new bonds. So we've got several bonds. Right? And that's going to also give us information about our enthalpy of reaction. And so we've got 3 different ways to do this on 3 different scales. Do you have a couple of equations that you know? Well, if I know that, then I can do Hess's law. Do I have elements and molecules in their standard states? And can I use that table? Right? So I've got something on molecules level. Well, then I can do that. Another way to do it is to look at the bond dissociation energy. So I'm going to take some bonds, I'm going to make some new bonds, takes energy to break bonds, makes energy to form bonds. I can figure out the sum of my breaking and the sum of my making to give us my overall energy. Right? So you would have a standard bond energy table, and in something like the reaction between hydrogen and chlorine to form HCl, we're going to look at the sum of our reactant bonds and the sum of our product bonds. And so we'll, because all these are in bond dissociation energies, notice that these are all positive, right? And we got to kind of do the math to make sure it works out, right? So we'll take our reactant bonds minus our product bonds. Here we broke an HH and a ClCl, and then we're going to subtract 2 bond dissociation energies from the HCl bonds that we're going to form. So we have 1 mole times 436 kilojoules per mole. Only one of those. And we've got 1 mole and 243 kilojoules per mole. And then we're going to subtract 2 moles at 432 kilojoules per mole. And we end up with negative 185 kilojoules per mole. Right? So different ways to get at the same thing. Okay. Let's real quick look at some of our